everybody, this is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Today we are going to start the fourth module of linear algebra and calculus, that is functions of several variables. Now, in the earlier classes we have seen the functions of single variables and their operations and how to find out the derivatives and integrals of functions of single variables and what do you mean by the functions of single variables, all that we have learned in the last class. Now in the today's session we are going to learn what are the functions of several variables and what is how to find out the partial differentiation for the functions of several variables, and what do you mean by the difference between the ordinary and partial differential derivatives, and what is when the functions are said to be functionally dependent and when the functions are said to be functionally independent, and Jacobian transformation. And at last we are going to find out the maxima and minima of functions of several variables, which is a continuation of the earlier section, that is the maxima and minima of single variables. Now the functions of, let us start with what are the functions of two variables. The definition of the function of two variables is very similar to the definition of function of one variable. The main difference is that instead of mapping the values of one variables to values of another variables, we map the order pairs of the variables to another variables. And what are the functions of several variables? These are nothing but the functions from real numbers to the another real numbers, and which maps a single valued function x to the another single valued y. Suppose if you have a single valued function from x to the another single valued function y, such a functions are referred to as a single valued functions and can be readily visualized in the two-dimensional coordinate systems. Okay, and above each point x, the y-axis, we graph the point y, and we, of course, y is equal to f of x. By now we have seen the graphs of many such functions, and we need to extend the visualization process of multivariable functions, also referred to as a functions of several variables. Now, what is a partial derivative? When to use the partial derivative? And what is the difference between the ordinary and partial derivative? Okay, suppose if you have a function y is equal to f of x, y is equal to f of x. Here we can see that x is an independent variable and y is a dependent variable. When number of independent variables is only one, then the change of x with respect to y is nothing but an ordinary derivative. If suppose number of independent variables are more than one, that is, let us suppose that z is equal to f of x comma y. Here we can see that the z value depends upon the two variables x and y, where two x and y are independent variables. So z value is based on more than one independent variable. So the change of z is based on both the independent variables x and y. So in this case, instead of using the ordinary derivative, we use a partial differentiation, that is partial derivatives. So let us see what is the partial derivative, and by definition wise, suppose we have a function f of x comma y, which depends on two variables x and y, where x and y are independent to each other. Then we say that the function f is partially depends on x and y. Now, if we calculate the derivative of f, then that derivative is known as a partial derivative of f. If we differentiate the function f with respect to x, then take y as a constant. And if we differentiate f with respect to y, then takes x as a constant. That means whenever you are differentiating a dependent variable z with x, then y acts as a constant. And if you are differentiating z with respect to y, then x acts like a constant, just like a constant. So that is now the partial, we all know that the derivative is represented by d by dx. The partial derivative is represented by dou by dou x, dou by dou x, and it can be symbolized with f of x. Suppose f is a function, f is a function of x comma y. So we are differentiating f partially with respect to x, then it is represented by dou f by dou y, which can be written as fx. Similarly, if f is differentiated with respect to y, then we can write it as dou f y okay, as a suffix y. So if we are differentiating f, as we have only two independent variables, we'll get only two first order differential derivatives, that is f dou f by dou x and dou f by dou y. The second order partial derivatives, for this can be represented by that is dou square f by dou x square, that means f double x. That means whatever value you got here, again we need to differentiate with respect to x to get the second order partial derivative, and it is symbolized with f double x. Similarly, dou square f by dou y square is given by f double y. So we'll get three second order partial derivatives. The third one is dou square f by dou x dou y, which is obviously equal to dou square f by dou y dou x. So what I need to say is x, if you differentiate x first with respect to x, then with y, or first with respect to y, then with x, both are one and the same. That means they both obey the commutative law. So that is the partial derivative. So in conclusion, we can say that the partial derivative is applicable if and only if the number of independent variables are more than one. If you have one, we need to go for the ordinary derivatives. Okay, so the limit, the definition for partial derivatives, if f of x comma y is a function, f is partially depends on the two independent variables x and y, and if we differentiate f with respect to x and then and y, then the derivatives are called as a partial derivatives, and it can also be given as f of x is equal to dou f by dou x, which is equal to limit of h tends to 0, f of x plus h comma y minus f of x comma y divided by h, and this formula is called as a formula by first principles for the partial derivative. Similarly, the fy can also be given as limit of h tends to 0, where h is the difference between the 2 points, because here we have two different points, x and x plus h. So the difference between x plus h and x is nothing but h value. So these are the two different points. The rate of change of two different points is given by the difference between the 2 points. So limit of h tends to 0, f of x comma y plus h minus f of x comma y divided by h. So this is the formula for fy using first principles. So let us find out what are the rules. The rules are quite often they are similar to the rules of the ordinary derivatives, the product rule. We all know that the derivative, that is u into v rule, nothing but u into v dash plus v into u dash, and these rules are obviously they are same. Suppose u is the product of two functions f into g, where f and g are based on x comma y, then ux is equal to dou u by dou x, which is equal to g of x comma y as a constant, derivative of dou f by dou f with respect to x, that is partial derivative dou f by dou x, plus f of x comma y is a constant, and derivative of g with respect to x, that is dou g by dou x. Similarly, uy can be given as dou u by dou y, which is equal to g of x comma y into dou f by dou y plus f of x comma y into dou g by dou y. So these are called as the product rules. So let us see one example on how to find out the partial derivative, and this finding out the partial derivatives plays very important role in functions of several variables, because in order to find out the Jacobian value or maxima and minima for several variables, we need to know how to find out the partial derivative of a given equation of the given functions. So I have taken a simple function here. Determine the partial derivative of the function f of x comma y is equal to 3x plus 4y. 3x plus 4y. So the given function is f of x comma y is equal to 3x plus 4y. So to find dou f by dou x, dou f by dou x, what we are doing? We are differentiating f partially with respect to x. So we need to put y as a constant. So this, the second term acts like a constant. The first term we don't have any y value here. Okay, so keep y as a constant and differentiate the function. Therefore, dou f by dou x is equal to 3, because derivative of x with respect to x is 1. So this becomes 1 and this becomes 0. So the answer is nothing, this becomes 0 and the answer is nothing but 3 here, right? Similarly, to find dou f by dou y, keep x as constant and differentiate with the function with respect to y. So it can be represented by dou f by dou y. So which is nothing but dou f by dou y is equal to 4. Dou f by dou is again the same way, because we have 3x plus 4y, two different terms. In the first term we don't have y, and the second term we don't have x. So when you are differentiating with respect to y, obviously the first part will go to 0, and second part, the different derivative of y with respect to y is 1. So the answer is nothing but 4 here. So in this way you can find out the first order partial derivatives. And going to the second order partial derivative for the same functions, if you differentiate the constant again with any other variable, it goes to 0, right? Okay, because the example that I have taken is a linear function, so we don't get any second order partial derivatives here. So let us go for the another example where we can find out the higher order partial derivatives also, right? If find the partial derivatives of f of x comma y, which is equal to x square into y plus sin x plus cos y. It's a mixed function, that is we have a polynomial and a trigonometrical function. Of course it's a transcendental equation, what we got it. Now let's find out the all possible derivatives, partial derivatives for here, and we need to find out the partial derivatives because we have two different types of independent variables x and y here, right? Okay, so the first fx. So when you are finding out the partial derivative fx, that y acts like a constant. So fx, which is represented by dou f by dou x. So here x square into y, the derivation of x square, that is nothing but 2x. Y is a constant here, right? Just like kx, if you differentiate kx with x, what you are going to get? We are going to get k. Okay, so d by dx of kx is nothing but k. Same in the same manner, dou by dou x of x square into y is nothing but the y acts like a constant, and derivative of x square, which is nothing but 2x. So that is nothing but 2xy plus 2xy plus sin x. Here sin x, the derivative of sin x is nothing but cos x. Okay, and the third term is cos y. We don't have a x term in the third x variable in the third term, so it goes to 0. So the fx, that is the dou f by dou x, is nothing but 2xy plus cos x. Similarly, if you want, the second partial derivative, that is dou f by dou y, we need to find out the dou f by dou y. You can write it as dou by dou y of x square y, because the function is x square y sin x plus cos x, right? Okay, cos y. Now I am differentiating with respect to y. When you are differentiating partially with respect to y, x acts like a constant. So x square is constant here. Derivative of y with respect to y is 1 here, right? Plus the second term is not containing any y value, so you put it as 0. The third term contains y value. The derivative of cos x is minus sin y. So which is nothing but x square minus sin y is the first order partial derivative for the given equation, right? Okay, so let us see one more example. Find dou f by dou x, dou f by dou y, dou f by dou z. This is a function of several variables. I have increased the number of independent variables from 2 to 3. I have taken the 3 variable function here. So f of x comma y comma z is equal to x cos z plus x square y cube e power z. Now, whenever you want to find out dou f by dou x, so dou f by dou x is nothing but dou by dou x of the function. What is the function here? X cos z, okay, plus x square y cube e power z, right? With what variable we are differentiating? That is x. So when you are differentiating with x, obviously y and z both acts like a constant. So you can write x, the derivative of x is nothing but, and the cos z acts like a constant here. Cos z, we have to write it here. And another, the second term consists of 3 variables here, x square, y cube and z e power z. So x square derivation is nothing but 2x y cube e power z. So this is the first partial derivative for the given question. So now let us find out the second partial derivative, that is dou f by dou x, dou f by dou y. In the first term we don't have any x y value here. The first term completely goes to 0. In the second term we have y cube, which can be written as 3y square. So x square is a constant here. The derivative of y cube is 3y square. Okay, e power z is e power z itself, right? So this answer is nothing but 3x square y square e power z. Similarly, if you want to find out dou by dou z, the first term consisting of some z term here. So x acts like a constant. Derivative of cos z is nothing but sin z, right? Derivative of cos z is nothing but sin z, plus x square is as it is, y cube is as it is, e power z derivation nothing but e power z. So this is that is nothing but f z can be written as minus x sin z plus x square y cube e power z. So that is how we can find out the first order partial derivatives for the given question. Okay, these operations we can try for number of functions and improve the rapport, because we need to have this knowledge to find out the Jacobian transformation, maxima and minima, and of two variables and three variables in functions of several variables in this module. Okay, so thank you all children. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.